So, um, hello everyone. My name is Cody Trevillian. Um, I'm a PhD candidate from Oakland University. The work that I do is mainly in the field of sort of quantum magnetics. So I'd like to talk to you today about my latest work on this two-qubit magnon-mediated quantum gates. So before we get into that, we should really all be on the same page of, what is a quantum gate, what are qubits? So qubits are these two-level systems. Any two-level system can form a qubit. And in these systems, we have this sort of aspect of a superposition that we can put our qubits in. So that's what makes them a little bit better than bits. We can have any linear combination of these two states, 0 and 1. And in addition to this qubit superposition, we have qubit entanglement, which can be sort of thought about like a group superposition, wherein we have these novel states that cannot be formed by actually just can't be formed by regular qubits. So this is truly what puts qubits above the level of functionality that can be achieved with bits. And the reason I'm talking about this is because we can form universal sets, and I'll get to that in a moment. Single qubit gates are just these simple rotations of a qubit. You can think of this projection of the qubit state as that of a Bloch sphere. And in order to keep this operation unitary, you just simply rotate the Bloch sphere. And we can also then talk about this, these sort of single qubit gates in a controlled sense, where then we enter the realm of two qubit gates. So this control, the state of the control dictates whether or not the single qubit rotation is applied to the target. So if it's in 0, nothing happens. If it's in 1, then in this case, I'm enacting an X gate, and I'm showing a C0 gate because this is an entangling gate. The reason for this is that you can actually form any universal set of quantum gates. That is, you can describe any quantum operation with just a set of single qubit gates and any two qubit entangling gate. And there's many different types of qubits. And the point is that they have this sort of nonlinearity that is anharmonicity that can be enacted just with these different geometries of qubits. In particular, I'll focus on this transmon qubit because we've shown that we can take magnons, these spin waves that we've heard about, and actually excite the transition between the 0 and 1 states of the qubits. And so that brings us to what is called hybrid quantum magnonics. And this has been going on for actually just about a decade now. And we can control the resonance of these different aspects, either of the electromagnetic cavity we're putting our magnon in, or the resonance frequency of the Higgs sphere itself. And if you can see here, this is a very strong coupling that we can form between the qubit and the magnon systems. And there's a ton of different ways that these have been realized, from planar systems to cavity systems. So I'll focus on planar systems, but cavity systems also exist, and what I'll describe could potentially be realized in those as well. And in all of these, we're able to achieve this very strong coupling with this very large level repulsion that you see here. And so with this strong coupling between the magnon and photon systems, we can do some interesting operations and control this coupling strength by tuning these biased magnetic fields. And what I propose is a dynamic level of control. So these so-called dynamic magnon-mediated interactions, where our transmon resonance is this 5 gigahertz. We put in a magnetic element, and using some sort of a control line, we can dictate sort of when and how the two systems are coupled. And because I'm talking about 2 qubits, I'll add a second qubit to this model here, and we can describe it with a Hamiltonian of coupled harmonic oscillators. Here, these terms describe the resonant frequency of our qubit systems and the resonance frequency of the magnon system. You'll notice that this is time dependent, which will be important for designing different 2-qubit magnon-mediated quantum gates. Another important characteristic is that these coupling terms here that I'm describing are number conserving. We don't want to lose any of our qubit or our quantum information when we're performing these operations. So with just a simple linear ramp, we can take a quantum face and bring it from a blue superconducting system into the green magnon system. But then it becomes rather sad because if you notice, the magnon lifetime is a lot shorter than that of the average transmon lifetime. However, if we have 2 qubits in our system and we use this linear ramp, then our quantum face stays rather happy. We bring it from the blue superconducting system to the red superconducting system. However, this still enacts this sort of reset operation that I described with the single qubit, where the red superconducting face becomes green and then is rather sad pretty quickly. So this brings the question, how do we maintain the unitarity of these operations, which is necessary for these to be quantum operations? Well, we can describe this in sort of this way that I show here, where if before the operation, these systems are unentangled, then we want to make sure that after, the superconducting and magnon systems are unentangled from one another. So that is, during the operation, they can be rather entangled with one another, but as long as after the operation, we ensure that the qubit and magnon systems are unentangled, then we can describe this, the whole of this operation, as a unitary magnon-mediated quantum operation. And so, again, if there's anything left in our green superconducting system, we can see that this quantum face will become rather sad. So again, before and after, if these systems are unentangled from one another, it's okay that during this operation, they become rather entangled with one another, as long as afterwards, the qubit and magnon systems are unentangled. So that brings us to single qubit gates. So with just a simple pulse protocol here, by controlling the time of the operation and the frequency separation between the magnon and qubit systems, I can enact different levels of rotation. As long as I ensure that I stop this operation, this pulse, within the timing of a single period of rotation, then I can, by controlling the frequency gap during this operation, I can control the acquired phase, which means that effectively I can control the level to which this block sphere is rotated. So then that brings us to the question of, well, how can I do this with 2 qubits? How can I control this single qubit rotation if I now have 2 qubits in my system? Well, as long as we ensure that these qubits are largely separated in frequency, which would be necessary if we wanted to be using them in the quantum computing sense, we don't want any crosstalk between the qubits, then we can go back to this concept of the reset operation, except in this case, we're going to operate with the quantum face quickly enough that it doesn't become sad. And I'll describe that in this way here. So we have our quantum face in the blue superconducting system, and we quickly exchange it into our green magnon system. And by ramping the frequency up to the point where it's then able to interact with our red superconducting system, then as long as after this operation, whatever's occurring here, then as long as we ensure that these systems again become unentangled and my quantum face returns to the blue superconducting system, then what I do in between here is then determining how I'm like what kind of 2-qubit magnon-mediated quantum gate that I'm enacting. And this means that as long as I ensure that there's a lack of this 0-2 state here, that is, as long as I ensure that the magnons do not remain in this magnonic system after this interaction, then I'm enacting a unitary magnon-mediated 2-qubit quantum gate. And actually this can be described in this sort of a 3-step protocol that I'll only show you these really complicated equations here, but safe to say that by describing some sort of an interaction here, as we can see, there's sort of 3 steps. There's an initial frequency gap, then by like the initial frequency gap here dictates the shape of the rest of the interaction pulse that is necessary for this protocol to be a unitary 2-qubit magnon-mediated quantum gate. So if the input here, as in I'm enacting a Z rotation, the input is equal to the output that we would expect. Okay, all right. So then we proceed with our operation, and we can see that, again, this system has some population here, but then afterwards, the phase operation is applied. And again, by varying the frequency gap, we get different acquired phases. And this then checks off all of our things, all of our aspects of a universal set of magnon-mediated quantum gates. And I described mainly for you here this 2-qubit magnon-mediated quantum gates. So in conclusion, we have different protocols that we can design, and it's just another aspect of this dynamic magnon-mediated interactions. And I'm told that we have our another, she's not in the Zoom room yet. Okay, so one of our other presenters will be joining us soon, but if anybody has any questions, I can go back to my conclusion slide and happily take your questions. Do we have Inez yet?
Yeah, I think Ines is